Hi there. I've gotten a few questions about how to do the center of mass calculation for the Goblet project. So I'm going to make a video of going through this calculation for the example I came up with. And hopefully you can use this as a template for your own projects moving forward. So just in case you didn't see the previous video, this is a very crude drawing of the goblet that I'm trying to describe. It has this base, a stem, a bowl, and one way of talking about this goblet is by defining some function, which we're going to call f of x, that traces out a region, where together with g of x, when we rotate that region around the x-axis, the shape that we get is the goblet in question. So we want to have some function that talks about this outside piece. And it's usually easiest to make that a piecewise function. So we're going to say that between 0 and 1, this function looks like a line, which happens to be 5 minus 4x. Between 1 and some cutoff point, it's going to be some constant function. This cutoff point ends up being 4.592. That comes from asking, when does this circle piece intersect the straight line piece? We can find this geometrically, we can find this algebraically, a few other approaches like that. If you think about this for a little bit and you have no idea where this number comes from, let me know and I can try to walk you through that. Anyway, we're saying that between 1 and 4.592, our function is this constant function. And then from then on, the outside piece is this semicircle, which comes from this equation, which I got from using the fact that x squared minus y squared equals r squared. Okay. Similarly, this g of x is another circle arc, and that's going to represent the inside of our cup. Okay, so if all we wanted to know was the volume of this, which is a piece that you need to know, we want to integrate between 0 and 10 of all of the cross-sectional areas. So we're picking our direction, and we're looking at slices perpendicular to that direction. And for the most part, for a lot of this, those slices are going to look like circles. Since we're rotating this region around the x-axis, if we take a slice of it, the cross-section looks like a circle. So the volume, we're gonna say that between 0 and 5, the cross-sections are pi times r squared. Between 5 and 10, the cross-sections instead are going to look like a washer. So in this case, it's pi times big R, the distance to the further piece, squared, minus little r squared. All right. So if we actually want to calculate this volume number, we want to know what these things are. So this integral, because f of x is a piecewise function, it's easiest to break it up into its separate regions. F of x is defined to be this piece on a certain region, so we're going to integrate over that interval of pi times the function squared dx. Over this next interval, we're integrating pi times 1 squared dx, etc. So if we actually calculate, so this integral between 0 and 5 ends up getting broken up into these 3 integrals. And then this 4th integral goes over here. So if we actually calculate this, we're going to see that our total volume is 130. I have this out to 3 decimal places. That's probably a good idea. If you already did it and only use 2, that's fine. But 3 is probably a little bit better. One of the requirements for this project is that the goblet uses less than 150 units of volume. I believe I said cubic centimeters. So here we're under that cutoff, so we're happy. There's also a requirement that has to hold a certain amount of liquid. That would be a separate similar integral. I believe that for these numbers, it holds more than 150 cubic centimeters of liquid. But this video is talking about the center of mass. So if you remember, the center of mass is the moment of mass divided by the total mass. Well, we don't really know the density of this, but when doing center of mass calculations, that density term is actually going to end up dropping out as long as it's the same throughout. So when we say that the volume is 130, if we also just say that, let's say that the density is 1, then the total mass would also be 130. So the thing that we're going to be looking for is the center of mass is going to be the moment of mass, which we're going to calculate in a second, divided by the volume. Right. So if you remember from before spring break, the moment of mass is going to come from the exact same type of calculation, except you're also multiplying the integrand by the distance from some reference points. In other words, we're saying we're going to multiply by an x on the inside of each of these things. So what that comes from is we're saying if for a particular slice, we want to know what the moment of mass for that slice is, well, it's going to be the total area times how far away it is. Well, how far away it is always just going to be x. So we can calculate the moment by doing the exact same calculation we did for volume, except we're going to include an x term on the inside of all of these. So I didn't write it all out, but this integral we could find by, again, breaking it up into 3 pieces. And instead of the first piece being the integral from 0 to 1 of pi r squared, it would be integral from 0 to 1 x times pi r squared. And that pattern continues throughout all of this. And if I did my Wolfram alpha calculations correctly, I end up getting 679. Okay, so that is the total moment of mass. The center of mass is the moment of mass divided by the total mass, which in this case is the same as the total volume, which in this case ends up being 6.28. So what that's saying is the center of mass is about here, at a distance of 6.28 away from the base. This whole thing's not necessarily to scale. 0 to 5 should be the same as 5 to 10. Yeah, and that's how it goes. Okay, so my center of mass is what did I say? 6.28. And the concern is that if the center of mass is too high, the whole goblet is unstable and it might tip over. And the thing that matters is how big the base is in relationship to the height of the center of mass. So the way I set it up, my base has a radius of 5. So in other words, the base is actually pretty big relative to the height of the center of mass. So because of that, the whole goblet is pretty stable. The rule, or in the description, was that we want to make sure that the center of mass is not more than 3 times the radius of the base. So since 6.28 is less than 15, I'm good. Okay. So as far as the project goes, you want to say that in a sentence or two, and then reference some of these calculations. But this is what we're looking for. This is what I'm looking for when I say I want the center of mass, the ratio of the center of mass, of the height of the center of mass to the radius of the base to be no more than 3 to 1. That's what I'm talking about. Okay, so if you have any more questions, please reach out to me. You can post on the message boards or leave a comment in the comment section, because this is posted on YouTube, so we can use that. Okay.